So having learnt about this spin के बारे में आपने समझा लास्ट दो क्लासेस में एटलीस्ट। एक मिनट। Okay, so before moving to spectroscopic transition, learning about this angular momentum, learning about this origin of spin was very important, right? Because it is a very fundamental thing which every elementary particle has। मतलब कोई भी छोटा जो आपको जो फंडामेंटल पार्टिकल आपके ख्याल में आता है, एनीथिंग, इलेक्ट्रॉन, प्रोटॉन, न्यूट्रॉन, या फिर when we visualize light as in form of particles, photons, सबके पास स्पिन है। ठीक है, ये बहुत बड़ी गलती होती है। कई लोगों से इंटरव्यू में पूछा जाता है कि फोटोन का, लाइट का स्पिन होता है क्या, क्या एंगुलर मोमेंटम होता है? बोलते हैं नहीं, फोटोन हैज एंगुलर मोमेंटम, सो यू हैव टू टेक इनटू दैट फैक्टर। और उसी पे सारा स्पेक्ट्रोस्कोपी बेस्ड है। आप सारे सिलेक्शन रूल्स को देखेंगे, it is we are always trying to conserve the angular momentum in the process, and because photon has angular momentum, that has to be taken care of, it must be conserved। और उसी से सारा सिलेक्शन रूल ओरिजिनेट करता है। एवरीथिंग इज लॉजिकल, ऐसे नहीं है कुछ रूल ऐसे ही आ गया। दैट रूल इज अ व्हाट यू से कैन सॉर्ट ऑफ जनरलाइजेशन ऑफ अ ट्रेंड, कि एक ऐसा होता है, लेकिन वो ऐसा क्यों होता है उसका पूरा रीजन है। आपको रूल रटा दिया जाता है एक्चुअली, वो मैं नहीं करने वाला हूँ। आई एम नॉट गोइंग टू लेट यू मग अप। So that's how so you have to, if you understand the spin, if you understand these points, uh, how a dipole is generated during a transition, then everything is becomes clear that why this selection rule exists। Okay, so spin के बारे में हमने देखा। the origin as it was it was discovered during the experiment by Stern and Gerlach। Okay, what we saw with the experiment with the silver atoms, and they were trying to verify the angular momentum originating from the orbital motion, the orientation, the aspect of space quantization was they were trying to verify the space quantization. That is, the angular momentum can have only specific orientation in three-dimensional space, and that angular momentum till that time, the only source of angular momentum for electron was considered as per the Schrodinger equation, as per the wave functions that was their angular radial part. It was only the orbital motion that was visualized till that time, and once this experiment happened, they realized this is the origin of angular, there is another source of angular momentum, and that is spin, right? So that's how it came about. The two sources of angular momentum, one is orbital motion, another one is spin। Then क्या कहा और क्या कहा मैंने आपको? Yes, I also told you that when you begin learning about electron, you are told that it is just like a sphere and it is spinning about its own axis. It is rotating about its own axis, that is spinning. It is like a spinning top. Not anymore. Don't stretch that spinning top analogy to the that level. That will be wrong. And that's in that context I told you that yes, that was because the spin that we are visualizing for electron is an intrinsic property, right? It is always there with the spin. Okay, and if you visualize it as sphere spinning about its own axis, then you try to calculate the velocity, you'll find the velocity comes out to be higher than much 100 times larger than the speed of light. That's impossible. It uh, violates the principle of Einstein's special theory of relativity. So there must be something wrong the way we have been visualizing spin, right? तो वो चीज़ एक बड़ी चीज़ थी कि अगर आप स्पिन को एक तरह से, हालांकि इफ यू ट्राई टू कैलकुलेट द वेलोसिटी फॉर प्रोटॉन because both have same angular momentum, so you can, that will be less than speed of light, you know. It's the mass is 2000 times 1800 times less for proton. So but once you describe a concept spin, it should be treated equally for all of them, right? स्पिन को हम एक के लिए कहेंगे कि इसका स्पिनिंग टॉप के जैसा है, इसका नहीं है, ऐसे नहीं. So that was taken to be like it is this intrinsic angular momentum. So is originating because of a property called spin. Spin is just like a property, just like a mass and charge. So that thing taken into consideration. So again we can write orbital angle. So if for this kind of uh, angular momentum, so for spin also we can write a wave function. इसके लिए भी आप wave function लिख सकते हैं, but इसके लिए जो conditions होगी वो that will be different. So when you have particles circulating about a central point and a particle centering around the axis, so initially visualization के लिए जरूरी है कि आप about as a sphere consider करके उसको ये कीजिए, लेकिन उसको बहुत ज़्यादा दूर तक नहीं ले जा सकते क्योंकि आप रियलाइज करते हैं कि इट इज़ द वेलोसिटी, जो उसकी वेलोसिटी है लीनियर वेलोसिटी एट एनी पॉइंट is coming out to be much greater than speed of light. Okay, so then how do you actually visualize this thing? How do you treat spin as a thing? What this property is all about? So you know, rest of the things we have already learned. We have now learned that just like L quantum number, there is spin quantum number S, and ms is just like ml, there is a component ms which gives you the projection of along a z-axis, and spin angular momentum of electron is fixed. This because this quantum number s can have only one value, half. So electron, proton, neutron all have same value of spin angular momentum, same magnitude. Okay, and the z component is given by this, which can have ms can have value plus half or minus half. So and I also told you that keeping in taking into consideration the uncertainty principle. So there is uncertainty existing between the three components of angular momentum along x, y, and z. So if one of them is exactly known, then you are totally uncertain about the other two components. So because what we know from the quantum mechanics, the z component is fixed. That's how we talk about the three-dimensional quantization of about space quantization. From the knowledge of space quantization, we know that the z component is fixed. So if we fix the z component, we are totally uncertain. We know it with certainty. Then we are uncertain about the x and y component of the angular momentum. So in case of, so this is your angular momentum due to spin, and the component is here. This is your component along z. So this z component is to be so anywhere on the cone, if you place this vector, angular momentum vector, the z component remains same, but the x and y component are variable. So that if we draw it like this, we are taking into account both the things. So this is the correct representation of correct pictorial representation for the angular momentum that arises from spin, right? And if this z component is fixed, plus half or minus half, the negative side, so if it is pointing downwards, the z component turns out to be negative minus z, and so that's how ms h cross, this is ms h cross. So that's how you draw the arrows. And once you know these two hypotenuse and this thing, you can calculate the angle turns out to be 55 degrees. इजी है ना, इतना तो आसान है. सो इस तरह से आप कोण पे प्लेस करेंगे. ओके, एंड then this was the thing. You calculate the two sources of angular momentum, spin and orbital motion. From the orbital motion can have different magnitude of angular momentum as given by L, 0, which can vary as 0, 1 to whole numbers, and the z component along MLH cross. So this is fixing your orientation, right? In a similar fashion, you have contribution angular momentum coming from spin, which is fixed. The magnitude is fixed for given particle. When we are talking about electron, this value is half. It is not changed. It can't be changed. Remember, this is the one of the quantum numbers that is people miss out. Ordinary textbooks miss out on this quantum number. They straight away go to plus half minus half. Remember, you also now आप रियलाइज कर पा रहे हैं कि जो आप अप एरो डाउन एरो करते थे वो क्या था स्पिन एंगुलर मोमेंटम का z कंपोनेंट था, प्लस हाफ अप एरो डाउन एरो, that was representing the, whenever you were showing electrons being like this, up arrow and down arrow, you were actually conveying the z component of the, this is what, ये z component था ना, it was z component of angular momentum due to spin, due to momentum due to spin. स्पिन से जो राइज हो रहा है वो उसका कैसे है, वो टोटल एंगुलर स्पिन एंगुलर मोमेंटम का नहीं था, स्पिन एंगुलर मोमेंटम के एक कंपोनेंट का था z के अलाउंग, राइट? अप और डाउन जो दिखाते थे हम, लाइक दैट. सो वो प्लस हाफ माइनस हाफ आप पहले से जानते थे, आप शायद ये नहीं जानते थे कि ये हाफ भी एक होता है क्वांटम नंबर, दिस इज एस. सो कंपोनेंट्स और वही फिर मैग्नेटिक मोमेंट, इन when you apply magnetic field, that z component only will contribute to magnetic moment, and so you see the m is written, m is given because of that magnetic quantum. So magnetic quantum number, spin magnetic quantum number, name it's like that, given like that. Okay, so and then we for multi-electronic system we'll talk about this later, we'll go to that when we go to term symbols, inherent property of all thing. So what we now know is that proton neutrons also have spin half, s is equal to half spin with angular momentum 0. So you calculate the angular momentum, you will find it is 0.866 h cut. So that also means protons and neutrons and electrons all have same spin angular momentum. That means when you are trying to visualize them, one of them will be moving slower, one of them moving faster. So electron is lighter, so it will be moving faster. That's the point we discussed in last class. वही हम last class में discuss कर रहे थे कि वो कितना fast होगा, faster than light हो जाएगा, वो चीज़ हमने discuss किया last time. And so that from the classical point of view, if you start visualizing the particles, protons are moving, much slower as compared to electrons. Other elementary particles, there are certain elementary particles which have s is equal to 1, and for in our context it is we have to visualize photon and we call them spin 1 particle. So आपको पता स्पिन के बेसिस पे क्लासिफिकेशन है, स्पिन हाफ पार्टिकल्स इलेक्ट्रॉन because s is equal to half, spin 1 particle photon. Okay, and later on you will see that if you treat nucleus as a single entity, then that can also be sometimes spin 1 spin and other both is it twin. So spin half particles are fermions, half integral spin, that is called fermions. Particles which are having spin 1 particles, these are bosons, we call them boson. इस किसके नाम पे, सत्येंद्रनाथ बोस के नाम पे है, ठीक है. And this spin half, these are called fermions. So electron, proton, neutrons come into the category of fermions. So there are certain things that we learn. This bosons and fermions have undergoes special thing. So fermions and bosons, half integral spin fermions, and those with integral spin including zero are called bosons. So electrons and protons are fermions, photons are bosons. This is what we know now for sure. Okay, and as we know, whenever something is formed, nucleus is formed, some energy is released in form of light, something. So that energy released is the force that binds them together, and that, so we say that it is the fermions are held together by bosons. That entire universe exists like this. It is just a combination of fermions, so that what you see, what you are able to see, the matter are constituted of fermions, and amongst the matter, the particles are held together because of the bosons. So photon is what we say that in this universe, it is everything what you see is an assembly of fermions held together by forces conveyed by bosons. So just like electromagnetic force. So photon and electron, these are things that is important for you. Up quark, down quark, that also constitute protons and neutrons. So all these things will be important. We have learned about the energy of yeah, कि energy levels कैसे हम define करते हैं. How do you find the energy of a hydrogen atom? Hydrogen like atom, hydrogenic atoms means hydrogen like atoms. So H, helium plus, Li2 plus, so all these are hydrogen like atoms, right? So in सब के लिए energy is only a function of n square, and here the variable is z, proton. So only two things determine the energy of the orbitals. Now so if you have two energy levels, suppose hydrogen has, so you know, if the electron is excited, a photon comes in, interacts with the electron, and it appears here. It is excited up, it goes up. So that is something that we call absorption of light. So it happens, it's mu, light comes in and the electron is excited, goes up. So that is absorption. And the second picture would be that when you have this thing, electron is already here. If it um, come back to the ground state, it will, if it once it is excited state, it is unstable. It will tend to come back to the ground state. In the process, it will radiate out some energy that will be Hν. So a photon of this particular energy is given out here. This is emission of light, right? So this is something that we know, and this Hν must be equal to, in both cases, what we find the energy gap. Del E is the gap. Del E is the gap here also. So this, what we know now, that this gap, the Hν, the photon that is exciting it, so del E must be equal to Hν. Only then absorption will happen, and only then the emission will happen. So this is your, what we know as Bohr's frequency condition. Sorry, the Bohr frequency condition. So this must be satisfied at all times. This is what we know. So the first, when we considering hydrogen atoms, सबसे पहले लाइमन बामर सीरीज सबसे पहले आपने देखा. So that was emission of light. So we were talking about, so that is what was happening there, right? So things have to be correlated with the experiments. Whatever theory you develop must satisfy the observed results. It must explain the observed facts. Okay, so this is what we know now. So initially it appears that I can ask you that what do you know? What do you think? One, if the electron is in ground state 1s orbital of hydrogen, can it go to 2s? Can it go to 2p? Can it go to 3s, 3p, 3d equally? Is all these transitions are possible? Initially, it will look like that everything is possible. Sub transition, all transitions look like it's possible, but it's not like that. Why? Because photon has intrinsic spin angular momentum corresponding to s is equal to 1. This is what I have been saying. So when electron and photon are interacting, the angular momentum must be conserved. फोटोन तो एब्जॉर्ब हो गया, उसका एग्जिस्टेंस खत्म, तो अब जो उसका जो एंगुलर मोमेंटम था वो कहाँ जाएगा? वो इलेक्ट्रॉन, इट मस्ट बी कंपेंसेटेड थ्रू द इलेक्ट्रॉन्स चेंज इन एंगुलर मोमेंटम. सो इलेक्ट्रॉन का एंगुलर मोमेंटम चेंज होगा, एनर्जी चेंज हो गया, ग्राउंड स्टेट से एक्साइटेड स्टेट में गया, उसके साथ साथ उसका एंगुलर मोमेंटम भी चेंज होगा, और एंगुलर मोमेंटम इस तरह से चेंज होगा कि दैट इज इक्वल टू द angular momentum of photon. It must be equal to angular momentum of photon. So this is an important thing which we must always think of. We must account for the conservation. We are losing photon when the light is being absorbed. A photon is less, its energy is transferred to the electron. What happens to the angular momentum, spin angular momentum of the photon? That is also, so that change in, so electrons angular momentum also must change, and that should change in such a way that it conserves. So it should be equal. अब मतलब कहने का मतलब, जो change in angular momentum होगा इलेक्ट्रॉन का, that must be equal to the photon's angular momentum. Change in angular momentum of electron must be equal to the angular momentum of photon. What I am saying? So what an important conditions that I'm talking about is this. What I'm saying is that you have, let's say, 1s, 2s, 2p, then 3s, 3p, 3d. So all of these are there. So this is your energy level, energy axis. N is equal to 1, n is equal to 2, n is equal to 3. Now what I have been telling you, that what are the transitions that are possible. So when I tell you that here, is this transition possible, is this transition possible, is this transition possible, is this transition possible, which one is possible, or is this transition possible, किस पे जाएगा if a photon comes in. So what essentially I am talking about, let's take this first one, only 2s and 2p. So I am talking about this thing. So let the things change like this. When transition is happening, electron in 1s is going to 2s by absorption of photon, h mu. Let me call this h mu 1. Okay, h mu 1. We can also imagine another transition. This is 1, this is, and the second one is 1s to 2p. तो अब देखिए क्या है, what is the change in angular momentum? Spin angular momentum cannot change. For a particle it is fixed, it is constant. Spin angular momentum cannot change. So if I have to change the angular momentum of electron during this process, it can only change by through the orbital motion. So orbital angular momentum is going to change. Okay. So what is the change in angular momentum? Delta L here is 0. Change in angular momentum is 0, right? What is change in angular momentum in this case? When you are changing it here, delta L is equal to plus 1, right? So L is equal to L1 is 0, L2 is 1. So you are having an increase in the. Now calculate the change in angular momentum. In angular momentum, and what is this? It is under root 1 plus 1 delta L h cross. So this is your angular momentum, which is, again you can give, because it is 1, so 1 plus 1 h cross, right? Now this is an angular momentum of photon. It must be equal to, this thing should be equal to angular momentum of photon. angular momentum photon, s is equal to 1, so under root s into s plus 1 h cross. So angular momentum is again under root 1 plus 1 h cross. So both the angular momentum is equal. So here in this case the angular momentum change in angular momentum for electron is equal to the angular momentum photon, and we say that uh, the so here what is happening is that angular momentum is conserved and is conserved. Now think of the same thing. uh, so this process is okay, but here this is not so. Angular momentum is not conserved. The change in angular momentum is zero. So you are not able to account for जो फोटोन के पास एंगुलर मोमेंटम था उसको आप वो कहाँ गया, उसके बारे में आपको आप नहीं, यू आर नॉट एबल टू अकाउंट फॉर. स्पिन एंगुलर मोमेंटम कैन नॉट चेंज. ठीक है, इट इज फिक्स्ड. आई टोल्ड यू, जस्ट लाइक मास of electron cannot change, in the charge of electron cannot change, in the same manner spin angular momentum is also intrinsic property, it cannot change. Okay, so the only way the electron's angular momentum can change is the second contribution, that is orbital. So orbital angular momentum should change in such a way that it is equal to the photon's angular momentum. ठीक है, और इसीलिए now in the same way you can think of, if I ask you 1s to 3d, whether this transition is possible, why it will not be possible. If you think of now again conservation of, in the same manner you can answer this one, why this is not possible. Don't say that this is a selection rule. Explain in terms of conservation of angular momentum. That's the fundamental thing. Selection rule is only, there is a whole lot of explanation for this. There is a so we are basically following the sacrosanct principle of conservation of energy and conservation of momentum. So when we are visualizing this third case from 1s to 3d, what is happening? H mu 3. So the change in energy is h mu 3. Okay, change in angular momentum, uh, you can see this is, you can look at the delta L is plus 2, 0 from L is equal to 0 to L is equal to 2. So delta L is plus 2, the change in angular momentum photon. So this angle, this gives you angular momentum of under root 2 into 2 plus 1 h cross. Photon has angular momentum of 1 h cross, right? S is equal to 1. So this is not equal. Angular momentum is not conserved, right? So photon's angular momentum is not conserved here. So you have to look at the whole system and the angular momentum must be conserved. So when suppose an electron goes from 1s to 3d orbital, the angular momentum changes by 2 units. Delta L is plus 2, and so in, but the angular momentum of photon is much less, and so the angular momentum is not conserved. Not conserved. That's why this process is cannot take place. So this is not not possible, cannot happen. This is the essence that you must, essence of the whole thing. Why delta L plus minus 1 is allowed, why this process happens easily, whereas the others, any other change other than 1 will not occur. Primarily because the photon has spin, and it has angular momentum. So during the transition, the angular momentum must be conserved, essentially, which means the spin angular momentum of electron cannot change during the transition or any time. वो हमेशा just like mass or charge वो उसी तरह का fixed रहेगा. So the only way the angular momentum of electron can change is through orbital angular momentum, and so that essentially means the change in L must be by 1 unit. Change in L, the quantum number L, the magnitude of orbital angular momentum, must happen by 1 unit. Okay, so that's how delta L plus minus 1 comes about. So now we understand this point. I hope so. So when I talk about this now, it should be fairly easy to understand. Change in angular momentum must compensate for the angular momentum carried away by the photon. So when you think about of an electron in a d orbital making a transition to s orbital or vice versa, the photon is not able to carry the enough angular momentum in this way when it is moving from 2 to 1, 2 to L is equal to 2 to L is equal to 0. D orbital से S में आएगा. And similarly, in a similar way, when you are going from 1s to so when you are moving from 1s to 2s, then again there is no change in electron's angular momentum. You are not taking into account the photon's angular momentum, so you are not able to account for the photon's angular momentum. That is not being conserved here. So again, this is not possible. We say that the some spectroscopic transition are allowed. That means we are conserving the angular momentum, and that is stated in form of a statement, which is, we call it selection rule. So there's another thing that we have to look for. एक तो हो गया, so जब भी one is conservation of angular momentum, and the second thing is that there's a transition dipole that is developed during the transition, and it is, क्या होता है कि ये जो transition dipole develop होता है, ये dipole will interact with the electric field vector, and better is this interaction, greater is the absorption. जितना अच्छे से interact कर पाएगा electric dipole is developed, and the electric dipole interacts with the electric field of oscillating electric field of light. मतलब during a transition you have during a transition you have electric dipole is developed. This dipole, the dipole interacts with the oscillating electric field of light, right? And then we say that absorption occurs. कैसे एब्जॉर्प्शन होता है, ये इसको समझिए. पहले इलेक्ट्रिक डाइपोल डेवलप होना चाहिए, तब वो जब तक ये इंटरेक्शन नहीं होगा, सो development of an electric dipole is a fundamental condition for the interaction to happen. Once the interaction happens, the light will be absorbed. So this thing has to, when you realize this, you look for the conditions under which that a dipole is developed. There's certain condition under which uh, dipole may not be developed. So let's look at some of these points. Uh, Let me pictorially tell you. So let me take you to the picture. Before I go to the mathematics, let me tell you simple. See, I'll keep it simple. Selection rules. So without going into mathematics, I will tell you a very simple thing. What we are talking about here. Suppose this picture A represents a transition from 1s to 2s. Picture B represents a transition. The inner sphere, the first one, is the 1s and this is 2s. Similarly, this is 1s and this is 2p, p orbital. So essentially I told you, मैंने आपको क्या कहा कि इलेक्ट्रॉन जो ऑर्बिटल्स है, these are just waves. Okay, so when I say that electron moves from 1s to 2s orbital, इसका मतलब हुआ एक इलेक्ट्रॉन वेव, उसका प्रोफाइल चेंज हो रहा है और वो 2s इलेक्ट्रॉन वेव में ट्रांसफॉर्म कर रहा है. उसी तरह से व्हेन आई से दैट 1s इलेक्ट्रॉन गोज फ्रॉम 1s टू 2p, ऐसा कोई कटोरा या बर्तन तो है नहीं कि इलेक्ट्रॉन उठ के 1s में था पहले, इट वाज इन अ बॉक्स 1s, नाउ इट इज मूविंग टू अनदर बॉक्स 2p. नो, देयर इज नथिंग लाइक दैट. इट इज अ वेव. So now that wave profile changes into a new wave profile. मतलब string वही था, जैसे standing wave in a string. There is one loop, lowest energy, and then if you plug the string with greater strength, so it will transform into two loops. So that is so imagine something, a standing wave of one loop transforms into a two loop by giving some energy input. So that is the transition kind of thing that we are looking, कि एक जो वेव प्रोफाइल था अब वो दूसरे वेव प्रोफाइल में चेंज हो रहा है. जो स्ट्रिंग में वन लूप वाला प्रोफाइल अब टू लूप वाले प्रोफाइल में चेंज हो रहा है. वही चीज हमें यहाँ पे विजुअलाइज करना है कि there was 1s electron wave, now it is transforming into 2s electron wave. There was initially 1s electron wave which has a angular part of that electron wave look like a sphere. Now that changes into a two tangent sphere, which I told you, two tangent sphere, that's the wave profile. When it's okay, तो ये जो चेंज ऑफ प्रोफाइल है, वेव का प्रोफाइल चेंज हो रहा है, अप एंड डाउन जो क्रेसेंट ट्रफ था, साइन ऑफ वेव फंक्शन. सो नाउ यू नो this is uh, so this is what is happening here when 1s to 2s moves. You see, it is symmetric migration of charges. Here it is, what we are seeing here is there is symmetric migration of charges equally in all directions. So no electric dipole develops. There is no electric dipole that develops. But here, in this case, it is asymmetric migration. You can clearly see that of charges and a dipole. Whenever there is asymmetric migration of charges, a dipole is developed. Can you see this? Now it can this dipole can interact with the electric field vector and the transition can occur. So this is another selection rule, which this gives rise to another selection rule, a statement. जो statement है उसके पीछे का explanation है ये, ठीक है? A dipole is developed, interacts with what? Electric field vector of light, and absorption occurs. absorption of light, transition, or you say that transition is happening, transition happens. But 1s to 2s, there is no dipole developed. This is not possible because there is no dipole is developed. The charges are migrating in a same fashion, same symmetry is retained. उस केस में डाइपोल डेवलप ही नहीं हुआ तो इलेक्ट्रिक फील्ड वेक्टर के साथ इंटरेक्ट ही नहीं करेगा, और इंटरेक्ट नहीं करेगा तो एब्जॉर्प्शन होगा ही नहीं. So essentially you can see when I say that asymmetric migration of charges is happening, you can clearly see one thing here, that so please visualize this, of one electron wave transforming into another wave. Exactly this, something like you have one loop in the string tied to both ends, a standing wave of, and then by some energy it is transforming into two two loops of things. So that is the kind of thing that happens. So whenever you have things like that happening, you always look for whether a dipole is developed or not. Remember, so you have electron, यहाँ पे कैसे चेंज हो रहा है आप देख रहे हैं. इलेक्ट्रॉन डेंसिटी was spherically symmetric initially in case of 1s. When it changes into, so when a 1s electron wave changes into a 2p wave, so what we say, when 1s electron wave changes into 2p wave, 1s electron wave transforms into 2p electron wave, dipole is developed, and this dipole, this is called transition dipole. This is and this transition dipole interacts with your electric field. Now this thing, so ये ब्लू वाला एरिया देखिए, यहाँ पे इलेक्ट्रॉन डेंसिटी है, इनिशियली है, और जब ये p वेव 2p में ट्रांसफॉर्म होगा, दिस इज 2p, 1s से 2p जब ट्रांसफॉर्म होगा, यहाँ पे इलेक्ट्रॉन डेंसिटी खत्म हो रहा है. तो जहाँ पहले इलेक्ट्रॉन डेंसिटी था अब वहाँ पे नहीं है सिमेट्रिक एरिया में, और यहाँ पे इलेक्ट्रॉन डेंसिटी कम था वहाँ पे अब ज्यादा हो गया, यहाँ पे आ गया. So this is what we mean by asymmetric migration of charges. Whereas look at the 1s to 2p, there is no transition dipole, symmetric migration of charge. Equally the charges, जहाँ पे चार्ज पहले था वहाँ पे अब भी है, जहाँ पे इलेक्ट्रॉन डेंसिटी पहले थी. सो यहाँ पे आप क्लियरली देख सकते हैं कि ब्लू वाला लेयर जहाँ पे था वहाँ इलेक्ट्रॉन डेंसिटी इनिशियली थी, जब वो 2p में ट्रांसफॉर्म हुआ इलेक्ट्रॉन डेंसिटी वहाँ उसी स्पॉट पे नहीं है. So this is clearly an asymmetric migration of charges which gives rise to transition dipole. So here it is symmetric migration of charges, no dipole. Transition dipole not developed. And that's why we do not have anything happening like this. So this is the second selection rule. Actually this is the first one. So we say that 1s electron wave transforms, it becomes a 2s electron wave. There is spherical migration of charges, no dipole is developed, and it is, we say that this transition cannot happen. In the second case, 1s electron wave 1s electron wave becomes a 2p electron wave, and in this process there is asymmetric migration of charges. A dipole is developed, dipole interacts with the electric field vector, oscillating electric field of light, and the absorption happens, the transition happens, right? So that's how you account. So there are two reasons now. If I ask you why 1 is to 2s is possible, sorry, not possible, while 1 is to 2p transition is possible. Then there are 2 points on which you have to answer. One is the conservation of angular momentum, that we saw, first thing that we saw. Okay, and the second thing is the development of transition dipole. 2 points, and that's how if I ask for explanation, don't write the selection rule and say this is the selection rule and this is done. It is following the selection, this is not following. No, explain in these terms the way I have told you. There's thorough explanation for everything. It is only a generalization of a thing, how it happens. And so we are basically accounting for conservation of angular momentum, and the this selection rule that we have just discussed. So one selection rule tells you about how you can conserve the angular momentum. The other tells you under what conditions a transition dipole will be developed, and when the transition dipole is developed, it is an electric dipole, remember. So this electric dipole can interact with electric field of the light, and that's how it happens. Everything happens. So development of electric dipole is essential condition, without which nothing will happen. So this is now we'll see. So we'll talk about the mathematics in the about the same thing in the next class. So this whole thing that schematically that I have told you through pictures is, this is told in terms of mathematics. There is certain things that will come up. So the mathematical part of the same thing will be discussed in the next class. Thank you.